Lecture 4 covers Section 3.1. At the end of today's lecture, you should be able to understand the formulation of moments in 2 and 3 dimensions. You should also be able to determine the magnitude of moments, as well as the direction of rotation, i.e. the axis of rotation of the moment. Lastly, you should be able to understand the vector product, which is also known as the cross product, and how it relates to the formulation of both couples and moments. When we analyze a point, there's no distinction between a body or a surface for it. For instance, a point, since it has no mass distribution within space, experiences the same force. Now, when we analyze a body, say shown in the figure to the right, which is a collection of points, we have to have a distinction between forces, because these forces can cause our body not only to translate, but also rotate about a specified axis. And we call this tendency to rotate about a specified axis a moment. Now, let us consider a body, for example, a bicycle wheel, where point O represents our axle. That is, this is a point where our wheel will be constrained. And we're going to take this as the body center. Now, if we apply a force to the tire at point A, we can say this force is acting about the center for body O. And this force acts some distance r, which is known as our moment arm. Now note, we know this force is going to cause the wheel to rotate about O, and it's also going to have a tendency for our body to translate in the direction of the applied force. To determine how this force causes rotation, we will decompose this force into a normal and a tangential component. The normal component is designated F sub n, and our tangential component is designated F sub t. Now we're going to define the angle theta between our line of action of r and our force. For a generalized two-dimensional case, such as this bicycle wheel, the magnitude of the moment about point O, which is represented by the variable m subscript O, is expressed as the magnitude of our moment arm times the magnitude of our force times sine of the angle between the line of action of our moment arm and force. Now we note that F sub t, the tangential component of our force, is simply F times sine theta. Therefore, we can say the moment about point O is Ft times d, where d is our perpendicular distance between point O and the line of action of f of t. Now our moment is going to have units of Newton meter. Now we see from this diagram that only the tangential component of force is going to cause a tendency for this wheel to rotate. The normal component of force causes no rotational tendency. Now what happens if we change the magnitude of f while keeping theta constant? Obviously, the magnitude of our moment about point O will increase. What happens as we change theta while keeping f constant? Well, as theta increases from 0 to 90 degrees, the magnitude of the moment is going to increase. And what happens if we change the diameter of the wheel while keeping our force and theta constant? Well, the magnitude of the moment will also increase. The magnitude of our moment measures the tendency of this force to make our body rotate about a fixed axis. And this axis of rotation is also known as the axis of the moment. If our applied force causes a counterclockwise rotation, like we saw in our example, our moment is positive, i.e. our axis of rotation is going to be the k-hat direction, and we're going to designate this as a counterclockwise arrow. If f causes a clockwise rotation, our moment is negative. That is, our axis of rotation is a negative k-hat direction, or we use a clockwise arrow. Now, our axis of rotation is determined by the right-hand rule. If we take our right hand and curl from our x-axis to our y-axis, i.e. in the direction of our force, we see our thumb is sticking out of the page, which would be the positive z-axis. For the figure on the right, if we curl from our y-axis to our x-axis, i.e. following the direction of our force, our thumb is pointing into the page, i.e. our negative z-axis. Let us determine the moment of force about point A in this example. Say we have a crane tower that is 40 meters tall and 30 meters wide. We have a 20 kilonewton force applied at point C, and we have two 20 kilonewton forces applied at point D, one in the positive x direction and one in the negative y direction. And for us to determine the moment of force about A, we have to look at these forces acting on their respective moment arms. If we begin, we recognize that the 20 kilonewton force at C does not contribute to our moment. That is, if we drew a line of action from A to C that represented our moment arm, we'd see that line of action would be collinear with our 20 kilonewton force. That is, sine of theta is equal to 0. Now we can look at point D. We have 20 kilonewtons acting in the positive x direction by a moment arm of 30 meters. That is, if we curl our fingers from our 30 meter tall moment arm in the direction of our 20 kilonewton force, we are going to be pointing into the page, i.e. we have a clockwise rotation. That's going to result in a negative moment. Now if we look at the other 20 kilonewton force that's acting in the minus y direction, it's acting on a moment arm of 30 meters as well. That is, if we curled our fingers from our 30 meter moment arm in the direction of our 20 kilonewton force, pointing in the minus y direction, once again our thumb is pointing into the page, and we'd have a negative moment. Therefore, calculating the moment of force about point A, we have minus 20 kilonewtons times 30 meters plus minus 20 kilonewtons times 30 meters, where now our moment of force about point A is equal to 1200 kilonewton meters, and its direction of rotation is clockwise, i.e. in the minus k hat direction.